Hello students, welcome back for new session of your crash course class, and this time we'll be covering or we'll be doing system of particles and rotational motion. I hope you people are preparing for your NEET 2026. So I wish you good luck, and shall we start? So we have system of particles and rotational motion. So it begins with your center of mass. So we'll be writing center of mass as short form or abbreviated form CM instead of writing it completely again and again. So what do you mean by center of mass? So we'll put up few theoretical conceptual points before we get into the numerical part of the center of mass. So for a point mass object, point mass body, center of mass is the point itself. So if you are given a small point mass, then that point is the center of mass. It means center of mass is defined for a distribution of point masses. So as the very first point says, if I give you a point mass, so that point mass is the center of mass. So center of mass is point itself. Then for what we define center of mass? So center of mass is defined for a distribution of point masses. It is defined for a minimum two point masses. Got it? So in that distribution you should have minimum 2 point masses. Now let's define for a distribution. So let's suppose you have a distribution. This is, if I define this point to be as your center of mass, so it is defined as a point where whole mass of the, either you call it as a distribution or a system, so it is defined as a point where the whole mass of the distribution is supposed to be concentrated. So Aditi, very good morning. Ram Kishan Verma, very good morning. So we have just started a concept of center of mass. So it is defined as a point where a whole mass of the distribution is supposed to be concentrated. Then for symmetric distribution, center of mass is point of symmetry. So if distribution is symmetric, then center of mass is point of symmetry. So let's suppose if you have a uniform ring distribution, this is the center of mass for a uniform disk, this is the center of mass. Maybe if you have a uniform square plate, so this is the center of mass. So all these points are point of symmetry if you have a symmetrical distribution. Now, so when you say for two particle system, so let's suppose if you have two particles M1 and M2, right? So for this two particle system, center of mass lies on the line joining centers of 2-point masses. It means for this distribution, center of mass will always be on this line, will never be like this and this. So center of mass is like on the line joining the center of the two masses. If these two masses are equal, if M1 is equal to M2, then center of mass would be the midpoint. Got it? If M1 is greater than M2, so if M1 is greater than M2, center of mass would be closer to M1. Got it? So and vice versa. So it means we have very interesting property. Center of mass lies closer to heavier distribution. So this is another feature. Now for random distribution, if your distribution keeps changing, fluctuating or time varying, center of mass is also not fixed. So if distribution keeps changing, then center of mass would also be changing, will keep changing. Now center of mass behaves the same way as original body or distribution behaves. It means whole body can be replaced with center of mass. So all these are theoretical, conceptual clarity about the word called this center of mass. So we can also understand if the original body can be replaced with this center of mass, it means laws or rules of physics which are applicable to body are equally valid for center of mass. So whatever laws you have in physics which you can apply it on a body, they are equally valid for your center of mass. Center of mass may lie within or outside the actual distribution. So it may lie within the actual distribution or it may lie outside the distribution. The best example is ring, where mass is uniformly distributed over its circumference, but its center of mass is at the center of the ring, and at the center of the ring there is no actual mass lying. So center of mass is, again, it's not a mass, it is defined as a point, coordinate point, where the whole mass of the body is supposed to be concentrated. Got it? So center of mass may lie within or outside the actual distribution, and the best example is ring. So these some of the conceptual or theoretical points about center of mass will help you to understand, to solve and to apply the concept of center of mass in varieties of numerical situations. If you have any doubt, please confirm it. Okay. Now, so let's apply two particle system. So let's suppose you have a coordinate frame x and y, and you have mass m1 which is at a position vector r1, and let's suppose its coordinates are x1 and y1. Then you have another mass m2, coordinates are x2 and y2, and its position vector is r2. Then center of mass of this system. So center of mass would be somewhere here, that would lie on the line joining these 2 point masses. So let's suppose if this is your center of mass, so this is, so center of mass, position vector of center of mass is given by m1 r1 plus m2 r2 divided by m1 plus m2. Because this is again a coordinate point, so it also has x and y coordinate. So x coordinate of center of mass is given by m1 x1 plus m2 x2 by m1 plus m2. Similarly, its y coordinate of center of mass is given by m1 y1 plus m2 y2 by m1 plus m2. Got it? Now let's suppose we extend it to 3 particle system, or maybe for n number of particles we have. So position of center of mass, we can extend it to m1 r1, m2 r2, and it goes up to mn rn divided by m1 plus m2 plus this, and this is up to mn. We can simply put it in summation form, mi ri summation of mi. So this is the position of the center of mass, and if you have a continuous distribution, right, the same formula can be extended to its integral form also. Now, for continuous distribution, we can put x coordinate of center of mass as x into dm by dm. Similarly, y coordinate can also be written as y into dm over integral of dm, and you know this integral of this dm actually represents the total mass of the distribution, and similarly you can put it the z coordinate also. Okay, fine. So now let's move to some basic numericals. Let's suppose if I have HCl molecule, got it? So you have hydrogen and you have chlorine. So let's suppose they are separated by some, we'll be doing some generalized numericals, will not be putting the numerical values here because all these formats will help you to solve the numericals. So now we have to find out the center of mass of this distribution. We know center of mass for this particle, this is a 2-coordinate system, got it? So how you will find out the center of mass of this 2-coordinate system? So let's suppose, because chlorine is heavier than this, the mass of chlorine we can put it as 35.5, whereas mass of hydrogen atom is simply 1 only. So center of mass would be closer to the chlorine part. So let's suppose this is x and this is r minus x. So if I keep this center of mass position as the origin, so this coordinate is 0. So what you will do is x coordinate of center of mass is m1 x1 plus m2 x2 by m1 plus m2. So if I put this coordinate as 0, so that gives you m1 x1 is equal to minus m2 x2. Minus sign indicates one is on the right hand side and one is on the left hand side. So one particle is on the right hand side of your center of mass, the other one is on the left hand side. So let's suppose this is mass of hydrogen, so it's 1, and this is r minus x, and this is 35.5. Will not be considering negative because we have already discussed negative means one particle is on the right hand side, one particle is on the left hand side of this center of mass position. So 35.5 times x. So if you know the value of r, that general separation between these two atoms in a HCl molecule, you can easily find out x, and that would define the position of center of mass with respect to your chlorine atom. Any doubt? Good. So this is the very first basic numerical you have. You can put it in generalized form also, like if I say this is m1, this is m2, and this is r, got it? So let's suppose center of mass is here, so this is x, this is r minus x. So going by the same fashion, m1 r minus x is equal to m2 into x. So m1 r is equal to m2 x plus m1 x. So that defines x as m1 r by m1 plus m2. Got it? So this is a general format. Now you can have any value of your m1 and m2. So I think Ramji, are you okay now? Aditi, Himanshu Chauhan, okay. Now let's move to 3-particle system. Now take one more example. Let's suppose we have an equilateral triangle and 3 masses m, 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 and this is A, this is A, this is A. Got it? So now we have to define the center of mass of this configuration. So how we'll approach, how we'll go ahead. So let's suppose if we define this one as my x and y coordinate, because this mass m is at the origin of your reference frame, so we'll put it as 0, 0. Can you give me the coordinates of this mass, second mass? Can you give me the coordinate? So its coordinate is, x coordinate is a and y coordinate is 0. Can you give me the coordinates of this one? Now look at this, because this is an equilateral triangle, so this is a by 2 and this perpendicular is root 3 by 2 a. So its coordinates are a by 2 comma root 3a by 2. So once you have x1, y1, x2, y2 and this is your x3 and y3, we can easily put the values. So what is the x coordinate? So this is m1 x1, m2 x2 plus m3 x3 divided by m1 plus m2 plus m3. Got it? So let's find out the value. So this is m, what is the x1? x1 is 0, m2 is this, x coordinate is a, m3 is also a and its x coordinate is a by 2 divided by 3m. You got it? Any doubt? So can you work out with this part? M cancels out and a plus a by 2 by 3. So that means 3a by 2 by 3. So that gives you a by 2 as the x coordinate. Now if I ask you the y coordinate for this, can you give me the y coordinate? Yes. So what is this y coordinate is? m1 into y1, m2 into y2, m3 into y3, the whole divided by 3m. So that defines your y coordinate. So any doubt from this part? Sure? Shall we move? Now let's move to a 4-particle system. So now we are keeping all these 4 masses as different masses. So this is, let's suppose, a square of side A. Now if I ask you how you will find out the center of mass of this, can you give me the center of mass? Will it be the center of the square? Had it been like this, m, 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 then center of mass would have been the intersection of the diagonals. So this is quite simple. Got it? Right? And you can easily say this, all these coordinates are a by 2 and a by 2. So that is quite easy. But now if you have 4 different masses, then again going by the same fashion, you have to put the coordinates. So this coordinate is, this coordinate is, this coordinate is, and the coordinates for this is 0, a. Now once you have all the 4 coordinates placed intact, give me the value of x coordinate of your center of mass. Yes, Aditi, good Sharan. Okay, so this is m1 x1, m2 x2, m3 x3 and m4 x4 by total mass, and total mass is 3 plus 3 plus. So this is the x coordinate. Similarly for the y coordinate, it is m1 y1, m2, y2, m3, y3, m4, y4 by total mass as 10 m. So that defines your x coordinate and your y coordinate of your center of mass. So this is for distribution. So center of mass is again defined for distribution of point masses. So you have calculated for 2 particle, for 3 particle, for 4 particle system, and this is how we can go ahead and we can apply it. Now let's find out for certain continuous mass distribution. Take the example of a uniform rod. So you have a uniform rod of mass m, length L. Got it? Now this is a uniform rod, so I will not get into the derivation part, rather I can simply put it, because this is a uniform rod, its thickness and density is uniform all through the length, then center of mass is the center. So center of mass is at L by 2. Got it? So shall we begin from this point? Now let's suppose you have 2 rods. So this is rod ML and this rod is also mass M, length L. So these are 2 perpendicular rods now. Now you have to find out the center of mass for these 2 rods. So for these 2 rods, what is the position or what are the coordinates for this system? It consists of 2 perpendicular rods. These 2 rods are uniform and equivalent rods. So each of mass M, length L. Now we know this is L by 2 and its y coordinate is 0. For this rod, its x coordinate is 0 and its y coordinate is L by 2. So center of mass would be somewhere here only. So what is the x coordinate of the center of mass? So this is m1 and let's suppose this is x1 and this is y1. So x1 is L by 2. For the second one, its x coordinate is 0 and this is 2m. So that defines as L by 4. Similarly, going by the same fashion, its y coordinate also comes out to be L by 4. So if you have perpendicular rods like this. Now let's suppose you have 3 rods. So 3 rods, each of length L and each of mass M. So if these 3 rods are placed or arranged like this, then what is the center of mass? So please go ahead, giving you 1 minute to solve this. Giving you hint. So this is your x coordinate, this is your y coordinate. So just simply replace this rod with this, its center of mass. So its center of mass is at L by 2 and y coordinate is 0. This is how. And for this one, its x coordinate is 0, y coordinate is L by 2. And for this one, its x coordinate is L by 2 and its y coordinate is L. Now once you have written all these coordinates for the uniform rods, then you go ahead with the formula. So how you will find out? Put the values and get me the answer, please. So this is m1 x1, m2 x2, m3 x3 divided by the total mass. Similarly, for the y coordinate, it's m1 y1 plus m2 y2 plus m3 y3 whole divided by the total mass, that is 3m. So this is how you will be attempting for the continuous mass distribution of 3 rods arranged like this. Any doubt from this part? Let's move to one more configuration. So 3 rods, each of mass m, length L. Now give me the x coordinate and the y coordinate of the center of mass for this configuration also. Good, Aditi, good. Now for this one, again mass is m, so x coordinate is this, y coordinate is this. For this one, its x coordinate is 0, y coordinate is L by 2. For this one, its x coordinate is L and its y coordinate is L by 2. So now once you have all the 3 coordinates, you just need to put the values in the given formula. So this is m1 x1, m2 x2, m3 x3 by total mass. Similarly for the y coordinate, so it's m1 y1, m2 y2 and m3 y3 divided by total mass 3m. Got it? Now let's suppose we have one rod, mass is m, length is L. We have another rod, mass is m, length is L, and now they are inclined at an angle theta. So you have 2 rods, again 2 rods, each of length L, each of mass m. Now give me the x coordinate and the y coordinate for this configuration. Now again for this one, its x coordinate, its y coordinate. Now its center of mass is at this position. Now let's define its x coordinate. So if this is L by 2 and this angle is theta, so its x coordinate is L by 2 cos theta and its y coordinate is L by 2 sin theta. Got it? So now for the x coordinate of the center of mass, m1 x1, m2 x2 by 2m. For the y coordinate, it's m1 into y1, m2 into y2 by m1 plus m2, so that gives you 2m. So I hope so you got the expression how to find out the center of mass for this configuration. Got it? Shall we move? Now you have a concept of disk. So again we are defining a uniform disk. Uniform disk, a disk which is of uniform thickness, uniform density all throughout its distribution. So you have a uniform disk So let's suppose its mass and its radius. So center of mass for this uniform disk is m. And you know how you write down m. So m we can put it as, if let's suppose if sigma is uniform surface mass distribution, so mass can be written as its area into, so mass m per unit area is your this one. Got it? So this is how we'll put down mass as this. So mass is directly proportional to radius square. We are assuming thickness is almost negligible, otherwise we could have taken the thickness also in defining this. So now this is the center of mass for a uniform distribution. This is the basic concept. Now let's suppose you have this r by 2. So let's suppose a disk of r by 2. This part is cut and removed. Initially your center of mass is at this position. Got it? Now if you look at this conceptually, look at this part. This part is uniformly distributed above the line and this part is uniformly distributed below the line. So this center of mass will not be disturbed along the y-axis, rather it will be, because once you remove this, so how you are left with is, the disk is something of this part. So you are left with this portion of the disk. Got it? So it means we know conceptually, because once you remove this part of the disk, then this part will be the heavier distribution and center of mass lies closer towards the heavier distribution. So center of mass will shift towards this side. Do we understand this point or not? So the part which is removed, so this part which is cut and removed, and we know m dash is directly proportional to r square by 4. So this is primarily this part is m by 4 only. You got it or not? So the mass, which is the portion of the disk which is cut and removed, so center of mass will get displaced towards this side, towards the heavier distribution. Do we understand? Let's label this one as x1, whereas the center of mass of the cut part lies here. So let's label this part as m2. Oh, sorry, this x2, and the part which is cut is m2, and the part we are left with is m1, and this value is x1. Do we understand this one? So I'll be giving you a shortcut to attempt this part. I will not get into the detail. So whenever you have this kind of situation, so we simply put it as m1 x1 equal to m2 x2. So m2 is the part which is cut and removed, and this mass we know is m by 4, and x2 is this original center of mass, and this x2 is primarily given to you as r by 2 only, and the part m1 which is left out mass, so original mass of the disk was m, so the part which is cut and removed is m by 4. So what you are left with is 3m by 4, and it gets displaced by this value x only. So we have to find out this x1, the x, that means center of mass will get shifted towards heavier distribution, So we have to find out this one. So this is how it goes. So x comes out to be r by 6. So center of mass will get shifted by value 1 by 6 times its radius. So this is a very famous numerical which have been asked number of times. So now we got the way how to attempt this, and that too is in a very shortcut way. So any doubt from this part? Okay. So let's suppose you have two discs. Mass is m1, radius is r1. Mass is m2, radius is r2. Let's suppose this is the origin. Got it? These discs are of uniform masses. Let's suppose it may have some thickness also. So mass m1 can be written as, so this is area into thickness. So area into thickness becomes volume, volume into density will become mass. So this is how we'll put m1. So where t is the thickness, rho is the density, and these two are of same material. So similarly we can put it m2 as pi r2 square, same thickness and same material, same density. So now if this is origin, then center of mass will be m1 x1 plus m2 x2 by m1 plus m2. So x1 is 0 for this part. So the first part goes. So this is m1 into 0. For m2, m2 is pi r2 square thickness into rho into, so this coordinate x becomes r1 plus r2 by m1 plus m2. So this pi is common, t is common, rho is common. So this is r1 square plus r2 square. So these common features will cancel out each other, and what you are left with is your x coordinate of the center of mass for these two discs. You got it or not? Let's suppose if instead of disc you have two spheres, then their masses can be written as 4 by 3 pi r cube. So volume into density. You got it? So similarly for m2 part we can put it as 4 by 3 pi r2 cube into density, and we'll go by the same fashion because this is still assumed to be at origin. So x coordinate of center of mass, so m1 and this part goes with 0. So what you are left with m2. So m2 is 4 by 3 pi r2 cube into this part, and its x coordinate is by, we simply put 4 by 3 pi rho common, and this is r1 cube plus r2 cube, and this common feature cancels out, and what you are left with is the x coordinate of the center of mass for this one. So Kushagra Raheja, very good morning. So any doubt? So initially we assumed it, we solved it for two discs, then we assumed it if you have two spheres, then how you go ahead with this, and this is how you will be solving it. Moving to next. So now we have motion of center of mass. So if two masses having position vectors m1, mass is m1, position vector r1, and the second mass m2 having position vector r2, its center of mass is given like this, then if you differentiate it and you just rearrange it, so center of mass, the velocity of center of mass can also be written as m1 v1 plus m2 v2 by m1 plus m2. And if you differentiate it further, the acceleration of center of mass is m1 a1 m2 a2 divided by m1 plus m2. Got it? So these are the standard expressions. So let's suppose you have mass maybe 1 kg, let's suppose, moving with velocity I cap plus j cap meter per second. You have another mass m2 that may be 2 kg moving with velocity I cap minus j cap meter per second. Then what is the velocity of center of mass? So we simply put it as m1 v1 plus m2 v2 divided by m1 plus m2. So m1 is 1 and v1, so this becomes I1 plus j1 and the other becomes 2I1 minus 2j cap divided by m1 plus m2, and that gives you 3. So that means 3I minus j by 3. So that is the velocity of center of mass. You will be just putting the values in the formula. So let's suppose you have another situation where m1 is moving with 1 meter per second. Let's suppose this m1 is 1 kg and you have 2 kg which is moving with let's suppose 2 meter per second, or let's define it as 0.5 meter per second. What is the velocity of center of mass? Now if you look at this mass is moving towards the right hand side, so its velocity v1 will be taken as positive. So this is 1 times 1. m2 is 2. Now this mass is moving opposite to v1, so that is towards the negative x-axis. So we'll put it as minus 0.5, and m1 plus m2 again gives you 3. So that means 1 minus 1 gives you 0. So center of mass for this configuration, for this system of two masses moving towards each other, so in this situation would be 0. You got it or not? Now let's suppose you simply have the idea about the Atwood machine, where you have a pulley, then you have masses m1, m2. So let's suppose if m1 is greater than m2, and we know m1 is greater than m2, so this mass will come down, this mass will go up. So what is the acceleration of the system? So acceleration of the system, I am not talking about acceleration of center of mass, it's acceleration of the system. So this is m1 minus m2 by m1 plus m2 into g. But for the same situation, if I ask you the acceleration of center of mass, then for this situation, so we'll keep it as m1 a1 m2 a2 by m1 plus m2. Got it? And we know if one particle is coming down, the other particle is going up. So they both are opposite in direction, and when you put the values, so acceleration of center of mass will be m1 minus m2 by m1 plus m2 whole square into g. So this is the formula for the acceleration of the center of mass of this configuration of this system. Now any doubt from this part? Now we have one or two conceptual cases now. So let's attempt one conceptual case. So we have a container. So we have a spherical body of mass m, and this is, let's suppose, filled with maybe water or sand, whatever it is. Got it? And this is completely filled. Its center of mass is initially at the center of this. Got it? Now, if your water starts leaking from an orifice at the bottom, so you allow this mass or this water to fall. So what you observe, so this water level keeps decreasing. So it means initially the water, when it was completely filled, the center of mass was at the center of this spherical bowl. But once this water starts falling down, it starts leaking, the level of water keeps decreasing, and you have center of mass will keep shifting towards the heavier distribution. So will keep lowering towards the heavier distribution. Yes or no? So it starts coming down, and when it is fully empty, center of mass will bounce back to its initial condition. It means center of mass will again be the center of the spherical container we have. So this is how the whole situation behaves. Any doubt from this part? So we have another conceptual situation. Let's suppose you have a bomb which may be projected with this. Got it? At the highest point, this bomb, at its highest point of its trajectory, this projectile bomb splits maybe into n number of particles, maybe 2, 3, 4, or whatever it is. Then, now first we need to understand, because the explosion is purely because of its internal factors, there is no external force involved. It means its momentum will remain conserved. As such, there is no external force. It means initially when the actual situation was, center of mass of this bomb before is following this parabolic trajectory. Even after explosion, the position of center of mass will follow the same trajectory. Even after explosion, the center of mass of the splitted systems, all the splitted particles will also have one center of mass, and that center of mass of the system will continue to move along the same parabolic path, and hence will complete its trajectory. Any doubt from this part? Now, we have a very important situation. This is a situation of a plank. Let's suppose we have a plank of mass m. Its center of mass is this one. Then you have a man standing on the plank and having mass m. So because mass is, this man is at one edge of the plank, so for these 2 point masses, so center of mass would be somewhere here. So this is the original center of mass of the system. Now system consists of 2 masses. One is plank of mass m and man of mass small m, which is at one edge. Now if man starts walking on the plank, and let's suppose this length is L. So no external force, so linear momentum has to be conserved. So position of center of mass will remain same. It means to keep the position of center of mass intact, the very same, plank will shift towards left hand side, and when man reaches at the other end, center of mass would still be the same, and this is how the plank gets shifted towards left hand side by value x. Got it or not? So what is this x is? Again we'll go by the same formula, m1 x1 is equal to m2 x2. So let's suppose this is man of mass small m, x2. Now though man has travelled length L of this plank, but its relative displacement with respect to ground is L minus x, and this is the plank which gets drifted or gets moved opposite to this. This is value x. So when you solve this, so this is mx plus small times mx, which is ml. So x we can put it as ml by m plus m. Got it or not? Kushagra Raheja. Last slide for the inclined plane example. What was that inclined plane example? It's basically not an inclined plane example, it is like an example of a projectile. So if you allow this bomb to explode at the midpoint or maybe even in the middle of the path, then even after explosion, just to conserve the momentum, the center of mass would continue to follow its same path. So that was the situation. I hope this is clear now, Kushagra. So this is how you have this situation, ml by m plus m, where m is the mass, small m is the mass of the man, L is the length, and capital M is the mass of the plank. Got it? Now let's suppose you have this mass m and this mass is small m and this is L. So when this slides, right? So again, when it slides, it will shift by value x. Got it or not? So situation is something like this. So if I have to find out x, so going by the same concept, so it's ml by m plus m. So instead of L, if this is theta and this length is L, right? So again it will shift, and this can be written as ml cos theta by m plus m. No sir, that acceleration at center of mass. Kushagra, that was, you just put the values a1 and a2, because a1 is like one is coming down, one is going up. So both have the same magnitude, but direction wise they are opposite. So when you just keep the values intact with the same magnitude, but in the opposite direction, you will end up with this formula. You got it or not? So these are the again two more competitive cases we have. Now you have one situation. Let's suppose you have this mass. You have one man standing at this position. You have one man standing at this position of the plank. You got it or not? And let's suppose this is M3. If this man starts moving towards this side and this towards this side, this is the extreme situation. If they simply exchange their positions. So this is M1, this is M2, and this is M3, and this length is again L. Got it? So let's suppose, just to keep this, M3 shifts by some value, yes or no. So this, let's suppose this is x. Got it? So what is the displacement of m3 with respect to x? Let's call it as delta x3. So delta x3 is x, and that too is on the negative side, and displacement of m1, we call it as delta x1. So this was delta x3. So this delta x1 is, this is L and this is L minus x towards positive side, and for the m2 the displacement, let's suppose, is delta x2, and this is L plus x, and that too is on the negative sign. You got it or not? Now, as you know, position of x coordinate is m1 x1, m2 x2 and m3 x3 by total mass m1 plus m2 plus m3. So for the change in position of the center of mass, we simply put it like this. Got it? So this displacement of the position of the center of mass is 0 because there is no external force involved. So we simply put it as m1 delta x1. What is delta x1 is L minus x. What is m2? m2 is the mass of the other one, and that delta x2 is m3 is towards negative side, and this is equal to 0. So when you know m1, m2, m3 and L, you can extract the value of x. So let's suppose if this x, which we have initially assumed to be as negative x, if it comes out to be positive, it means the whole of the system is adjusted and move towards the other side. It will compensate the direction as per your mathematical calculation. Any doubt? Okay, so this was all about this part. Now we have, so moving to the next stage, so that was all about your center of mass. Now coming to the concept of torque. So torque is written as R cross F. So that means moment of force is known as torque, and torque is basically that brings the particle to in rotational motion about its fixed axis of rotation under this applied force F, right? So let's suppose if I apply a force of I cap plus j cap plus k cap Newton, and its position vector is 2I cap plus j cap minus k cap. Now I have to find out torque. So to define torque as R cross F, so we simply go by your cross product method. So we know this is cross product. So torque is perpendicular to your this vector R, and it is also perpendicular to your F vector. So I j k, so R cross F, so this is 2 1 minus 1 and F is 1 1 1. So how you will find out? So simply you drop this one and this one. So this is 1 minus minus 1. So this is your x cap plus j cap. You drop this one. So this is minus 1 minus 2 minus 1 and 2. And for the k part, you drop this and this. So this is 2 minus 1. So that defines 1 plus 1 as 2I cap, minus 1 minus 2 gives you minus 3 j cap, and that defines k cap as Newton into meter. Got it? So this is all about your torque part. Then we have concept of angular momentum. So angular momentum can also be understood as r cross p, and we know torque is dl by dt, rate of change of angular momentum with respect to time is also understood or defined as torque. Got it? Now we have moment of inertia. So moment of inertia is written as I, which can be written as mk square. So this is a scalar physical quantity where k is known as radius of gyration. This moment of inertia depends on mass of the body and its distribution with respect to your fixed axis of rotation. Got it or not? So let's define. You know physical significance of moment of inertia. So it means if you have a larger value of I, the bigger value of I, it means you need to have a bigger value or a larger torque is required to change its state of rest, state of motion, or state of motion, uniform motion about its fixed axis of rotation. So this is the physical significance, right? So let's suppose this is m1, m2. So if I have to ask moment of inertia of this distribution of this particle system, about an axis passing through its center of mass. So let's suppose this is the center of mass and this is how you are defining. So if in general r is the separation between these two masses, so again this is x and this is r minus x. Got it? So again m1 r minus x is equal to m2 into x. So that means m1 r by m1 plus m2 is your x only. Got it? So for this, let's suppose we call it as r1 and we call this one as r2. So if I label this as r1, so what this r2 comes out to be? So that comes out to be m2 r by m1 plus m2. Now I have to define moment of inertia. So that means m1 r1 square. So that means radius of gyration. Radius of gyration is perpendicular distance from this axis of rotation. So this is, oh, I think I have given a wrong notation. I should give it as r2 and this one I should put it as r1. So if I label it as r2, so this is r1. So m1 r1 square plus m2 r2 square. So what is m1? And when I put r1 square, so r1 square means m2 square r square by m1 plus m2 whole square plus m2, what is r2 square? So r2 square becomes m1 square r square by m1 plus m2 whole square. And when you rearrange it, so we'll take m1 m2 common, so m1 m2 common, then it becomes r square, so it becomes m1 plus m2 by m1 plus m2 whole square, and this whole square goes with this. So what you are left with is your moment of inertia of this two particle system about an axis passing through its this one. Got it? Now let's move to let's suppose we have a rod. Got it? So rod of mass m, length L, and this is again a uniform rod. So we have to find out moment of inertia about an axis passing through its center perpendicular to its rod. So when you allow this, so it comes out to be ml square by 12. So moment of inertia of this uniform distributed rod about an axis passing through its center perpendicular to its length, so that is given by ml square by 12. Got it? And let's suppose if I have to find out moment of inertia about this axis, right? So let's suppose this is z axis, and if I call this one as iz, then we'll follow parallel axis theorem, and parallel axis theorem says moment of inertia about z dash axis is iz, which is primarily the moment of inertia about its center of mass also, which is important, plus m times h square, where h is this perpendicular distance between these two parallel axes. So this h is primarily L by 2 for this case. So this is and when you solve it, it becomes iz dash is equal to ml square by 3. Got it? So here this breadth or this width is assumed to be almost very small as compared to length. But let's suppose if you have breadth b, and now this is the moment of inertia. So moment of inertia about this axis, let's call it as maybe ix, iy, right? So if I call it as ix, so then this is mb square by 12. Got it? If I extend this to a lamina, let's suppose its length is L, breadth is B, right? So moment of inertia about this axis is, let's call it as y-axis. So this is ml square by 12. If I call this one as x-axis, so that is mb square by 12. Now if I have to find out moment of inertia about an axis which is perpendicular to its plane, so that means I am talking about iz. So I'll go by my perpendicular axis theorem. So that says ix plus iy. So this is ml square by 12 plus mb square by 12. So that gives you m by 12. Got it? So this is moment of inertia. Let's suppose if I have a special case where you have a square lamina where L is equal to B for so this becomes ml square by 6. Got it or not? So let's suppose this is your square lamina, got it, and its length is L only, and iz, which is perpendicular to its plane, So this is in square is defined as in xy plane, then iz is equal to ix plus iy. Got it? So let's suppose if I call these two axes as x and y as your diagonals, so ix and iy are also same. So this is your diagonal, so that means Iz by 2. So Iz for the square lamina was ml square by 6, so this becomes ml square by 12. You got it or not? Then you have a ring. So this is your ring. Ring is defined in xy plane. Mass of ring is m. Its radius is r. Got it? So moment of inertia about an axis passing through its center perpendicular to its plane, that is Iz, is given by mr square. Let's suppose this is one diameter, this is one diameter. So this may be x-axis, this may be y-axis. So Iz is equal to Ix plus Iy, and both are equal. So moment of inertia about its diameter is mr square by 2, right? So let's suppose if I have moment of inertia about tangent, and this tangent is perpendicular to plane. So this is Iz prime z dash. So this is Iz plus mh square. So this was mr square plus. So if you have another axis which is parallel to this, so this is perpendicular distance is r only. So that comes out to be 2 mr square. And let's suppose you have moment of inertia about tangent in the plane. So that means in the plane, let's call it as Ix prime. So this tangent Ix prime in the plane is basically diameter plus ms square, which is again, and that comes out to be 3 mr square by 2. Got it? Now instead of ring, if you have disk again in xy plane, then moment of inertia is mr square by 2 about an axis passing through its center perpendicular to its plane, and again about one of its diameter is mr square by 4, and moment of inertia about its tangent in the plane, that comes out to be mr square by 4 plus mr square. Moment of inertia about tangent, that is perpendicular to plane. So perpendicular to plane becomes 3 mr square by 2. Got it? For solid sphere, moment of inertia about one of its diameter, maybe solid sphere, so you may have diameter in any of the planes, so that means 2 by 5 mr square. Got it? So if you have about this which is tangent, so that becomes 7 by 5 mr square. If you have a hollow sphere, so moment of inertia for the hollow sphere is 2 by 3 mr square, and about this axis is 2 by 3 mr square plus mr square, so that gives you 5 by 3 mr square. Got it or not? So let's suppose you have a distribution like this. So basically these are the, and this is your axis. So this is sphere 1, this is 2, this is 3, this is 4. You can assume all the, I mean like 1, 2, 3, 4 configurations. You may assume it as ring, you may assume it as sphere, you may assume it as disk, or whatever it is. So what you want to, so let's suppose if it is ring, we have to find out moment of inertia of this system about this axis. So this is primarily sum of all the four. So if I assume it to be ring, so this is in the plane of the ring. You got it? So what is this moment of inertia for the ring, which is about its diameter? So this is mr square by, and 4 is also same. But for 2 and 3, this is like a tangent in the plane, and tangent in the plane is 3 by 2, and 3 is also tangent in the plane, and that gives you the moment of inertia for this configuration. Similarly, you can do it assuming it to be disk. You can do it even for solid sphere. You can do it even for this one, which is solid sphere or maybe hollow sphere you have. Got it? Now we have a disk. So disk of mass m, radius r, and this is in xy plane. So moment of inertia of this disk is, let's suppose original one is mr square by 2. Let's suppose a small disk of radius r by 2. So this part is cut and removed, right? So what is the mass of this part which is cut and removed? So this part is m dash r dash square by 2. So its radius, we know mass is still, because this is a uniform distribution, so m dash is, so which is m by 4. So this m dash is originally m by 4, r dash is r by 2, so that becomes this one. So what is the moment of inertia of the remaining disk? And that is simply I1 minus I2 we have. Got it or not? Now, so instead of from the concentric part, it is removed like this. Got it? So original I1 was I2, about its center of mass is same. Got it? So this is the part cut and removed. But now we have to find out I2 dash. So when you go and apply your parallel axis theorem, so this is r by 2. So this is mass of this part, which is m by 4 into h square. So h square becomes r square by 4. So this is I2 dash. So moment of inertia of the remaining disk is I1 minus I2 dash. So look at the difference. Look at the difference we have. Got it? Then we have conservation of angular momentum. Got it? So we know torque is dl by dt if no external torque, net torque acting on the system, then angular momentum of the system remains constant or conserved. Got it? Angular momentum L can also be written as I omega. So here we'll attempt one numerical. If Earth suddenly shrinks to 1/64 of its original volume, then its new time period of rotation is. So, because there is no external torque, so angular momentum of the system remains constant. So, I1 omega 1 is equal to I2 omega 2. So, Earth being a solid sphere, so we'll keep it as 2 by 5 m r1 square, 2 pi by t1, and this is 2 by 5 m r2 square, 2 pi by t2. So, mass being constant, so r1 square by r2 square is equal to t1 by t2. Now, because it's reduced to 1/64 of its original volume, so 1/64 of 4 by 3 pi r1 cube becomes 4 by 3 pi r2 cube. So, when you take the cube root, you got it? So, R2 is basically R1 square by 16, and this is T1 by T2, and we know T1, the original time period of Earth about its own axis is 24 hours. So, your T2 becomes 24 by 16, that gives you 1.5 hours. Got it or not? So, it means the new period of rotation of the same planet Earth would be 1.5. So, this is all about from my side for today's part. करने के लिए बहुत कुछ है बच्चों, but time does not allow us. So, I have tried my level best to teach you some of the important concepts and try to cover some of the important numericals. So, I wish you good luck for the NEET 2026. Now, your botany sir will continue with the next session. So, thank you very much. Thank you.